Welcome to Physics with Ben. In today's video, we want to look at calculations in specific heat capacity and latent heat. We have done so much on this topic. Visit the previous videos so that you can get more clarification. We are making use of this textbook, this and this. Without much wasting of time, let's go straight to the business of the day. Question number 11, New School Physics, exercise 9, page 236 to page 237. It reads, define I, specific latent heat of fusion. So we start. Question number 11. The specific latent heat of fusion is defined as the quantity of heat energy that is required to change a unit mass of a substance from its solid state to liquid state without change in temperature. And the SI unit for the specific latent heat of fusion is defined, is a joule per kilogram. From the equation H is equal to ml SFI. So the second question is define specific heat capacity. The specific heat capacity of a substance is defined as the quantity of heat energy that is required to raise the temperature of a unit mass of that substance by 1 Kelvin or 1 degree Celsius. From H is equal to mc change in theta. The small c stands for the specific heat capacity of a substance. The units for this guy is joule per kilogram per Kelvin. The next question is define thermal capacity. Thermal capacity or heat capacity is defined as the quantity of heat energy that is required to raise the temperature of the entire mass of a body by 1 Kelvin or 1 degree Celsius. From the equation H is equals to Cp change in theta, or from Cp is equals to what? Mc. These are the two equations for this guy. And the SI for this guy is the joule per Kelvin. Joule per Kelvin. Joule per Kelvin. Now, that is that for that. It is imperative as physics student, when you are asked to define any physical quantity in physics, you should state the equation, if there's any equation, also the SI units of the quantity. So this is the right thing to do. So let's solve the other part of question number 11. It reads, what mass of ice at minus 14 degrees Celsius will be needed to cool 200 cm³ of an orange drink, essentially water, from 25 degrees Celsius to 10 degrees Celsius. Specific latent heat of fusion of ice given to be 3.36 exponential 5 joule per kilogram. Specific heat capacity of ice given as 2100 joule per kilogram per Kelvin. Specific heat capacity of water given as 4,200 joule per kilogram per Kelvin. So first things first, what we are going to do now is what I call data collection. So let's begin. They say what mass of ice? Mi, mass of ice, is not given. Will be needed to cool. What mass of ice at? That is initial temperature of ice is given as minus 14 degrees Celsius. Wow, this is dry ice. We need to cool down, that is volume of orange drink, VOD, volume of orange drink is given to be 200 cm³. Mind you, we are going to convert this to meter cube. So what are we going to do? You are going to divide this the same thing as 200 200 divided by 100 raised to the power of 3. So 200 divided by 100 raised to the power of 3 will give us something like this. We have 200 divided by 100 raised to the power of 3. We are going to have 0.0002 meter cube. 0.000, that is 0.00 meter cube. So to minimize our space, we are going to say that this is the same thing as, let me minimize the space. We don't have much space here. We have volume of orange drink is 200 cm cube, and this is the same thing as 0.0002 meter cube. That is that for that. So we are done with this particular part. So the next thing is okay, I take it again. What mass of ice at minus 14 degrees Celsius will be needed to cool down orange drink of this volume? And that orange drink is essentially water from what? Let's call this theta 1 of the orange drink is 25 degrees Celsius, and theta cold of the orange drink is 10 degrees Celsius. Specific latent heat of fusion of the ice, LFI, is given as 3.36 exponential 5 joules per kilogram. 5 joules per kilogram. And then the specific heat capacity of ice is given to be 2100 joule per kilogram per Kelvin. And then the specific heat capacity of water, CW, is 4200 joule per kilogram per Kelvin. So these are the available data in the question. The next thing is I want to sketch this question so that you will understand what the question is all about. If you remember very well, in the other video I drew something like this. I call it the heating curve for solid ice. And so I'm going to do the same thing right here. Heating curve for solid ice. So this is my energy in joules, and this is temperature in degree Celsius. Temperature in degree Celsius. Now, if you watch that video very well, I did something like this. Let's start from this point. From this point, then you have dot. Then from this point to this point to this point, and then to this point. Let me make it more. Let me have more stick here. From yes, this is cool. So let's call this point A, point B, point C, point D, point E, and then point F. So we call this 0. This is 0 degrees Celsius. That is 0 degrees Celsius. So in 0 degrees Celsius, this 0 degrees Celsius, this is called the melting point. The melting point of the ice is at 0 degrees Celsius. So anything down here is dry ice. So this is -2 this is -2 -4 -6 -8 -10 -12 -14. -14 is down here. So this is what we have. So this ice was at this level. This ice was at this level. And the ice had to cool an orange drink that was at somewhere here. So from this point to this particular line, this is 100°C. I will call this point the boiling point. This is the boiling point. This is the boiling point of water. But then the orange drink was at 25°C. Somewhere here, let's put this here. 25°C. And then when ice at this level was dropped into it, it cooled down from 25°C down to 10°C. That's it. So I'm going to draw so let's trace this line back to this place. And this line back to this place. This is melting point, this is boiling point. Now, from points, our graph we are not making use of from here up. We are making use from 25 down. 25 down to -14. So the change in temperature from this point of 25 down to 10°C, the change in temperature here is given as a 25 minus 10. That's it. And then there's another change in temperature from 10 to 0 degrees. That change in temperature is given as what? 10 minus 0 degrees. And then there's another change in temperature from 0 degrees down to -14. And that change in temperature is given as what? Change in theta is given as 0 minus -14. So these are the change in temperature that we have. Now back to business. The heat responsible, the heat energy responsible, the heat energy responsible in raising the temperature of the ice from -14°C to its melting point 0°C is given as HAB is equals to what? Mass of the ice times specific heat capacity of the ice times change in temperature. In this case, you have your HAB is equals to mass of the ice, C of the ice into 0 minus 14. So from point B to point C, you have melting. That is the specific latent heat of fusion of ice from point B to point C. So we'll say that HBC is equal to what? MLFI. That is the specific latent heat of fusion that is required to melt this ice from solid to liquid at point C. At point B, you have both ice and liquid mixed together, but at point C, you have just what? Ice. So we say that AB is what? Solid. Solid, liquid, gas, or steam. Do you get it? So, now this is what will happen. We call this point, let's call this ABC. Let's call this C prime. And then let's call this point D prime. So from D prime to C prime, the orange drink lost its heat energy. And the heat lost by the orange drink from D prime to C prime is given as what? HDC prime is equal to what? mass of the liquid, because the orange drink is said to be a liquid. Mass of the liquid times specific heat capacity of the liquid times what? Change in temperature. In this case, your HDC prime is given as what? Mass of the liquid, specific heat capacity of the liquid into what? This change in temperature. 25 minus what? 10 minus 10 degrees Celsius. That is that. Now, the ice gain heat energy from point A to point B, from point B to C, and from point C to C prime. So the heat gained by the ice from cold water to what? 10 degrees Celsius is from point C to C prime. So we write that the energy here is H what? C prime is equal to what? Mass of the ice, specific heat capacity of water into what? 10 minus 0 degrees. 10 minus 0 degrees. So with this information, we are good to go. So what will happen here is that the ice will gain heat energy, and while the liquid, the orange drink, will lose heat energy. This is very cool, pretty cool. So let's write. We are about to solve the question now. Write from the principle of mixtures, comma, it implies that heat gained by ice in heating from theta I, that is in heating from minus 14 degrees Celsius to what? To theta cold. To theta cold. That is 10 degrees Celsius. Heat gained by ice in heating from minus 14 degrees Celsius to what? 10 degrees Celsius is equals to heat lost by orange drink in cooling from theta 1, that is 25 degrees Celsius, to what? Theta cold, that is 10 degrees Celsius. Heat lost by the orange drink in cooling from 25 degrees Celsius down here, that is from D prime to what? C prime, is this. So we are going to convert this statement into a mathematical equation. This statement is very, very, very important. So are we good? Yes, we are good. So let's write. Heat gained by ice, HGI, is given as what? Let's compute now. It's given as what? H. It's given as HAB plus HBC plus HBC plus H what? Plus CC prime plus HCC prime That is the heat gained by the ice. If we put in these variables, we are going to have, this is the same thing as what? Mass of the ice times specific heat capacity of the ice into what? 0 minus 14 plus mass of the ice. This is mass of the ice, Mi, plus mass of the ice, specific latent heat of fusion of the ice, plus HCC prime plus what? Mass of the ice, specific heat capacity of water into what? Into 10 minus 0 degrees. That is that for that. We can call this our equation number 1. Now let's write heat loss. Heat loss by orange drink, HLOD, is given as what? It's just this portion from D prime to C prime. Heat loss by the orange drink is given as what? It's given as HDC prime. HDC prime. HDC prime is the heat loss by the orange drink. And if we substitute, we are going to have something like this. We're going to have mass of the orange drink, which is mass of the liquid, times specific capacity of the liquid, times what? 25 degrees, 25 minus what? 10. So if we put all this into place, it implies that we're going to say heat gain is equal to what? Heat loss. So this implies that heat gained by ice is equal to what? Heat lost by orange drink. Heat gained by ice equals to heat lost by orange drink. So if we substitute correctly, we are going to have it as follows. So this implies that the whole of this, so we call this is heat loss by orange drink. We call this equation number 2. So we are going to equate equation 1 with equation number 2. So this implies that mass of ice, C of ice, into, if we say 0 minus 14, we are going to have what? 14. So into 14 plus mass of ice, specific latent heat of fusion of ice, plus mass of ice, specific heat capacity of water, into 10 is equals to what? Heat loss by orange drink, mass of liquid, specific heat capacity of liquid, or we can equally say water. Mass of water. Mass of water or liquid. See the same thing. Into what? 25 minus 10 will give you 15. Yes. 25 minus 10 will give you 15. 25 minus 10 will give you 15. So into what? Into 15. Into 15. So we are going to make mass of the ice the subject of the formula. This was what was asked for us to find in the question. So, but something is missing. We are going to look at that. We call this equation number 3. But then, the mass of the liquid is not given. However, the volume of the liquid was given. Now recall that density is equal to what? Mass over volume. So this implies that volume is equal to what? Density is mass over volume. Density is mass divided by volume. And this implies that mass is equal to what? Density times volume. Density is defined as mass divided by volume in the units of what am I saying? Sorry, volume over the mass of the substance. Yeah, density is what? Volume divided by the mass of the substance in the unit of what? Sorry, kilogram per meter cube. Yes. I was correct now. Sorry, mass over volume. I was correct. Yeah, density is mass of a substance divided by volume. So this implies that mass of a liquid is equal to what? Density times volume. That is it. Mass is density times volume. So it means that we are going to substitute this guy here. Can you see that? So and also recall that the density of liquid is given as 1,000 watts, 1,000 kilogram per watt meter cube. That is the density of liquid. Let me verify that quickly. Density of liquid 1,000. Yes, I was correct. 1,000 gram per kilogram per meter cube. So we are going to substitute the whole of this here. So it implies that the mass of liquid is equal to density of liquid times volume of liquid, which is the same thing as what? 1,000 times what? 0.0002. And the answer is 1,000 times 0.0002. The answer is 0.2. We have 0.2. Yes, we have 0.2 kilogram. That is the mass of the liquid. So come back here, right? Mass of liquid is given as what? 0.2 kilogram. Because of space, let me quickly clean this. So the mass of liquid is 0.2 kilograms. So we are good to go now. So we factor Ni out of this equation. So we'll have Ni is into Ci14 plus Lfi plus Cw into 10. That's it. It's equals to mass of liquid, C of liquid into 15. So this implies that mass of ice is given as the whole of this divided by the whole of this. Is mass of liquid, C of liquid into 15 divided by C of ice times 14 plus Lf of ice plus Cw of water into 10. So this is what we are going to do. So the mass of the ice is given as 0. We now substitute 0.2 times 4,200. That is specific heat capacity of water times 15 divided by specific heat capacity of ice 2100 divided by 2100 times 14 plus latent heat of fusion of ice times plus 3.36 exponential 5 plus 4,200 times 10. If we do that correctly, we are going to have this. So mass of ice is giving us, let's do it one by one. We have 0.2 times 4,200. 0.2 times 4,200 times 15. If we do that, we have 12600. Divide by stage by stage. Let's say 2100 times 14. If you do that, you have 29,400 plus this plus 3.36 exponential 5 plus 4,200 times 10. We have 4,200. So we add everything together now. So we have 12600 divided by this plus this plus this. So let's calculate. We have 29400 plus 3.36 exponential 5. I want to verify if that is actually exponential 5. Yes.